So we have already had a discussion of our logs structure storage. So we'll do some recap here. So basically, log structure storage are required for wherever that it's very write heavy uh, scenarios. So where we can will directly write the data instead of compared to the B trees where we have to get that particular location and update it in place update. So this has a quite advantage. So basically, LSM tree has like a two components. One is like in memory, another is disk based storage. Uh, in memory is known as a mem table, where it's not immutable. Basically, it's immutable where the data gets updated in particular location. But once there is some certain threshold which gets uh, reached, so that will be flushed to the memory that basically into the storage, which is the immutable. Uh, Since so we can have a multiple copy of the this storage. So we in certain time, like after some time period, we if in frequency we have a compaction where multiple what do you say this component stored component is merged in and made into a single one. Then then we have already discussed this on Tombstone, where we're going to uh, delete any particular record, how we are going to uh, mark it that this is deleted. This was the basically discussion in the last. Then we were like reconciliation, all these things we have discussed last week. So basically, this all the discussion where whatever we discussed were mostly were the logical structure of the LSM tree. Today we'll start with the mostly like how in the disk this gets stored, right? So what all the things we're going to cover today? So we start with the SS tables, where like it's a sorted like it data gets stored in a sorted order, right? Uh, this will start with again, then we'll go to the Bloom filters of how to efficiently find the data, how where in which LSM trees have been stored, right? Then we'll go to the skip list. The skip list is basically the linked list uh, where we can find efficiently the data in a logarithmic complexity instead of a linear time complexity. Then we'll go to the compression, where we compress the data before flushing into the storage. Then we'll move to the Bitcask and Wisckey, which are kind of ordered, like ordered. Till now, we have uh, discussed the unordered one. We'll discuss the ordered one. This is like a Bitcask and Wisckey. Then we'll discuss the concurrency, log stacking. Basically, log stacking is like um, what you say, like a we have a file system layer, then we have a database layer. So they can have their own bookkeeping, right? They can manage their own way. So this is known as log stacking. There are certain benefits and disadvantages if you don't use it properly. Then we'll move to the FTL, how uh, we can avoid the disadvantage of this log stacking. And then we'll at the end we discuss the this one, llama and mindful stacking. Let's start with the this SS table. So in SS table, as we discussed, right? So this is the like sorted in like it's a sorted data record is stored. Uh, Whatever the data record is coming, it's stored in the in sorted order in the disk. And the index files we have, right? Like indexes are there, which is going to point to that sorted data record. This index file can be of like either a B tree or a hash table. B tree, like also like is good, same way. B tree can help it to identify that data lookup, and same for data file also. Since this is a sorted order, even if for hash table also we can it can support the range queries. So comparison. So here there is a comparison like in case of hash table and uh, like whenever you're using hash table and this one B trees, hash table has always like as we know a constant lookup time, right? And in case of B tree, this will be always logarithmic one. So in hash table, how are you going to find out? Basically, we'll find the first uh, first that the key will be we're going to find with that for key we're going to get the value, and after since the data is in sorted order stored in a storage, we are going to get all the data after that, right? Because it's in sorted order. um, then compaction here also, then we can compaction and uh, compaction is there, which can, since it's in sorted order, it can read sequentially, and yeah, we can have it like it can sequentially, and I can have preserved the order. uh, Still now any doubt? Anybody want to speak anything?
I think in the last slide, we missed an opportunity to explain what compaction is. So like what
So
exactly?
yes, actually in compaction, what we do, since this data is in the ordered state, right? Stored in an ordered state, we read sequentially, right? And we start compacting all, and when compacting one by one, because since the data can be duplicated, right? Uh,
Yeah, highly.
Yeah, so the compaction process happens like in the background, right?
yes. Mm, shall we proceed ahead?
Yeah, I just wanted to.
Mm-hmm.
Yeah.
Mm-hmm. So yeah. So since we can have multiple this one like we LSM tree, right, in a disk. So to find out that our data is present in which particular location, right? Um, it's very difficult, right? So there are certain solution. One is solution is to have a range defined for each table, right? Till this range to this range, this particular data will be present here. But that also won't be sufficient because it can give the false result, right? In the both cases, whether it's present or not present. So it's not very precise in every case. So that's why we are using a Bloom filter here. So Bloom filter basically it can produce always the false positive, but it will never give the false negative result. So how it works, that to have a large bit of array, like considering one having 1010 like this one. So each we have a given, let's say, group of a hash function, and each hash function has a key. We're going to apply. We have to apply that key to all the hash function, and that is going to give a location. If all the location will have a one, it means the data is present. So, but it can be possible the data can't be present because it's can produce a false positive. But any one of the location has a zero, it means that for sure data is not present in our that particular uh, uh, LSM tree. Then next is the skip list. So skip list we use in the in memory storage. So skip list basically is the kind of linked list where like data is stored in a sequential order, but there is a one catch here. It's work like as a binary tree, not exactly the binary search tree. Um, so I got one beautiful image here. See, this is a skip list example one. Like we have a nodes like 10, 20, 22, 23 like this. Then we have one kind of express lane. So let's say we want to find the data, let's say 43. So instead of going to like this one sequentially searching the data, we have express lane where we can go to 10, 30, we go to 57. Okay, data will be before this 57, then we go to 30, one layer down 30. Then we can go search sequentially to 43. We'll get the 43 directly. Now, how many? Let's see how many records we have to scan. One, two, three, four. Instead of going with the whole all over the each record one by one. So this is the benefit of the skip list that using the logarithmic complexity we can find the that node easily. It's the height of the node depends on the some function based on the probabilistic height we maintain. And also we like B tree, we don't have to you do the rebalancing and all. This is also one example of the skip list. Let's say we want to find the like we want to insert the 17 number here. So step by step, what will be like? We will start with the initial node on the top. We'll go to the next node. We see 6. Since 6 is still smaller, we'll go to the next. It's nil. One layer down, we'll go. Then we'll go to the next node. We'll get a 25. 25 is greater than 17. So we'll again go to one layer down. We get the 9. 9 is less than 17. We'll go to 25. Then 25 is greater than 17. We'll go one layer down. We go to get the 12. After we get a 19, since we can't go, it's already we are the in lower level 0. So this is the place where we have to insert that 17. This till now this is clear, right, guys?
Yeah, it's a thanks. Okay. Highly, could you go over it again, I guess?
Yeah, please. Any questions? Or shall I proceed ahead?
Yeah, just like a quick question. Like, I guess it's kind of hard for me to understand. So, so if this was like it's a linked list, right? But like, how is it really different from a linked list? This diagram is, it's hard for me to understand, honestly. So could you maybe
it's like a linked list that is a tree. Well, I guess a linked list is already a tree, but it's like a linked list that is trying to reduce the amount of searches you have to do. So in a linked list, and I guess this could be achieved by using like a linked list and a hash map, to be honest. But in a linked list, like if you want to find a node, you have to start from the head and continue till you get to the tail. But they have created like a hierarchy here where from one node, you can use an express lane to go to some other nodes that is further down the line. And if that node is greater than what you're looking for, then you know that you want to like go down the hierarchy. So for example, I don't know, you're at node 6, you take the express lane to 25, but 25 is, I guess this implies like an ordering. So this is ordered in some way. So you get to 25, 25 is greater than the number you're looking for. So you have to go back to 6 and go down. And when you go down, instead of checking 7, you can check 9. If 9 is less than the number you're looking, sorry, if 9 is less than the number you're looking for, then you don't need to check 7 at all. And you can now use 9's express lane, I guess, to check for what you're looking for, and so on and so forth, right? So I think this is just sort of reducing the amount of searches you have to do in a linked list. Like, what the algorithm is interesting, but yeah, I think that's the idea.
Yeah, exactly. It does has a, like based on this logarithmic structure, this height, we like skip a certain amount of the uh, node ahead, and with the log n time, we can reach the exactly the place where we want.
Sorry, just to clarify, that means there's like the linked list, which contains like the data stuff, and there's like an auxiliary kind of linked list data structure too, which you go to first, which then helps you find where the linked list is in the chain.
I think it's more like there is or at least how I'm thinking about it. I mean, I haven't implemented this or anything, so don't quote me. But think of like a linked list, like the way a linked list works normally. So there's usually just like one pointer forward and one pointer backward in like a W linked list, right? For this one, I imagine like there'll be multiple pointers, like a node will contain multiple pointers. And one of the pointers, so imagine you have your previous and next pointers, but you also have another pointer that is like express or something, like you just call it express pointer. And this express pointer goes like further down the list so that it's like it can help you jump ahead of a couple of nodes further down the same linked list, right? And because it helps you jump, you can now do like comparisons with less searches. Does that make sense? So
yeah.
Yeah,
that makes more sense now.
all right.
Okay.
Yeah. Hi.
Yeah.
Yeah. Alaluwa, you can go. What's the question?
Oh, can you hear me now?
Yes.
Oh, great. So I don't mean to drag you guys back, but how would that be implemented if you have, say you have all these nodes now, and then you want to jump from, say the express line from 6, you want to jump to like say, oh, took that away. Okay, from 6 to like say 25, right? How would you do that? Like, I understand that would theoretically it kind of makes sense, but would you?
Well, I feel like there'll be some semantics, like you decide some things. I don't know the details about this. I don't know how you decide what the express node should be or what should be in the express lane. But let's just imagine we randomly pick, right? So, for example, in this, like the question you asked, how do you go from 25? Based on this picture, from 6, you can only, sorry, what did you say from 6? How do you go to 25? Is that what you said?
Yes, because there's a line from 6 to 25.
Yeah, so all you just need to do is like, there is a node that contains 6.
Mm-hmm.
You just point, so I'm going to send like a weird class structure.
Okay, that's fine.
The express pointer will just point to a node, the node that contains 25. Like that is all that needs to happen. But how do you go about knowing what node to point to? Like what express node should be? That would be like an implementation detail, I think. So you decide like what the best way to hop from one node to the other is for you. I guess.
Okay. All right, no problem. Thank you then.
Yeah. Yeah.
Isn't that where the probabilistic, nature of the skip list comes in? So you decide whether or not. So that's what determines the height of the chain. Then you can skip ahead.
Yeah, that makes sense. So you use like probability to decide what the like how to skip. Is that what you're saying?
Yeah, that in my head, like when I visualize it, that's kind of how it might be like not correct, but that's how I'm thinking of it. So
You know,
it's
it
like
makes sense, yeah. Because also like there are a couple of skips here that are not very that it's not like uniform as well, right? Like you're not skipping like every 2 nodes. Like for some you're skipping like, I don't know, 4 or 5 nodes. So yeah, maybe.
So the height is always decided by some. We have kind of some special function. I'm not sure it's a hash function or some probabilistic function. I haven't got detail in that, but there is one special function which is going to decide that height. But height has to limit at some point. It won't go beyond that.
Cool. Thank you. Yeah, that sounds good.
So we'll start with the compression here. Whenever the data gets flushed from the mem table to the storage, we compress the data and we store it, or even we when while compaction also we while doing the compaction also we compress the data. So the problem here is that if you see in the this particular image here, right? Uh, once compaction is done, right, the size can be reduced or from the actual block or page size. So we have to maintain like a table, offset table, where it's going to like have a specific location, like from where this particular page is starting and where the page is going to end. So this is going to help to identify where if you want to get that any particular data from the um, disk. So yeah, we'll start with the unordered. Till now, we have discussed the ordered LSM storage, where you're going to in this we're going to store where we were storing the data in order. So this first is the Bitcask, where data, like whenever the data comes, right, it gets stored in a whatever the it's like a when the data comes, it will be appended every time. So it will be it's not in a sorted order. It's like whoever came first, it will be going to store first. After that, it will be like going to get appended. Uh, Here we don't have a WL because this data only going to act as a WL here. And to identify the find the data, we have a in-memory hash map, which we called I don't know how to pronounce, like key directory, something like the key TIR, which is going to reference to the latest snapshot of that particular value of that key. Like you can see the example here. We have a multiple keys here, and the data, let's say key 1 came which is with value 1, then key 3 came with value 2. It keeps on appending here, and this hash map will always have contain the latest uh, like a snapshot of the link here. So let's say for key 1 there are key 1 with value 1, but it will but latest is the key 1 with value 3. It will point to the latest one. uh, at a certain point of time, it keeps on uh, removing the old data during the compaction by having the sequential read. Problem with this one Bitcask is like it has it's implemented the hashing, so it won't support the range queries here. So to overcome this one, we have a uh, Wisckey, WISC key. Hello. Yeah, yeah. Hari.
so just to clarify on the Bitcask
Hmm.
case, right? Like it can only support point queries because it's a hash map, right? Not
Yes,
really because, yeah.
yes, and also since it's See, as we have discussed in SS table, right? Using hash map, we can support the range queries. Why? Because that was in ordered, but this is, since it's not in ordered, we can't support it, right?
Right.
So
So
over,
the data
yeah,
is
I mean,
unordered.
I guess technically you can support it. It's just going to be really slow because I guess like you can just, if you want like from one key to the other, all you have to do is like find, like do like a lot of points, points queries, but that would be abysmal, I think.
correct. Um, okay, yeah. So to overcome this issue, like like since it's not able to support the range scan, we have Wisckey, WIC key. So here, instead of having hash map, we have a LSM trees, right? It's like a kind of, so at the leaf node, we're going to point the latest record of the uh, data, and this file is known as a here vlog files. We call as a vlog files, and it's this special type of file because um, see here also we have a same way we are going to append the data every time whenever the record new data is coming. Only the thing is that you don't have to scan all the file here because somehow they have a head and tail concept which going to reduce the whole scan significantly. So you don't have to scan all the vlog file to reduce like remove the older data. Uh, we'll discuss about the concurrency in the LSM tree, which are the point we have to keep in mind while this whole process, which are the point where this concurrency issue can happen. Um, so there are a few points where the concurrency can happen, where like whenever the mem table switch is happening, right? Let's say we, yeah, hello.
Hi,
Hmm.
sorry, just to confirm,
Hmm.
the Wisckey
Hmm.
allows range scans because the keys are sorted, right? So the keys are stored separately from
In
the.
a kind of LSM tree, so it you can have performance in skin, yeah, instead of a hash map.
Interesting. Okay, that's interesting. Cool. Thanks.
Right. So yeah, in case of LSM tree, concurrency can happen whenever the, let's say you are going to switch the mem table, right? Let's say you have a mem table which is going threshold has been reached, and now you want to switch it. So while switching, you have to create a new mem table, and the old one you need to flush it. That particular point you need to take care. Then this is the one thing. Then also then truncation of the write ahead log, where once the mem table is full, you're going to flush it data you to the storage. You need to truncate the WL also. This is the one thing where this concurrency issue can happen. In this book, one place like Apache can how this concurrency issue is solved in the Apache Cassandra is like it it waits for flushing until all the write is done. Once all the write is done, then you start with the flushing of the mem table. So this way, it won't let's say we there's a very less chance of what do you say desynchronization here because it will complete all the write before the flush. So synchronization issue can happen during compaction also in a storage, but there is a very that is not that much complicated. Um, Same way, we're going to hello, yeah, please.
Yeah, quick question. Is there a distinction, like with what you're describing, between synchronization and flushing?
So flushing is the No, there's a distinction. So flushing is when is the whole flow is this flow, right? Synchronization is can be the problem which can happen.
Uh, So synchronization is like a point where bad things can happen, and flushing is writing to disk, right?
Yes, yes.
Okay, yeah, that makes sense.
So yeah, during compaction, yeah, we are doing the same thing. Like old table will still remain readable, and once the compaction is completed, then will the new compacted table will be start reading happening with the compacted table, and old table will be discarded. Then we move ahead with the log stacking. So basically, log stacking, I will say like it's like uh, let's say we have a storage, then it has a file system, then it will we have, let's say, application layer, or you can say as a database layer. Each layer will have their own this log this LSS, like what do you say, buffering strategy. So this so because of this, lot of issues can happen. uh, we'll go one by one why all issues will happen here. uh, but why this log stacking, and why SSDs are like both are uh, made for each other, right? What so there is in SSD you can't do, like, if you do lot of write, right, in place write, so SSD's lifespan will be reduced. So that's why in a file system, what you do before writing, doing a write every time, we do buffer first in memory, and at a certain point of time, we'll flush all the data in a SSD drive. So by this way we can increase the lifespan of the SSD. But the problem here is because of this, uh, but it's not that much straightforward, right? uh, we need to have a we need to know, let's say, there are the block, yeah, like this. We have a block here. There are few places which these pages are empty, and few pages where the page which is alive, and few pages are discarded, and you want to uh, put the new data here. Now how are you going to put it? You so there FTL comes, flash translation layer, which is going to going to track all these pages, and they are going to copy the data from one block to other block. And once this block is like all the data is copied, it's going to uh, clear the block, so that new data can come here. So by this way we are reducing that in place, every time um, this the same page data is written. Any doubt, guys? Okay. We'll move ahead to file system logging. In file system logging, again the same issue we have here. Like each layer have their own LSS, and each they are not going to coordinate between each layer, right? And this is going to cause any issues, because of this segment size and all this fragmentation can increase. So and also, let's say, since this each layer has their going to buffer the data, they are going to maintain the for durability, they are going to maintain the WL. So that also going to create cause the fragmentation. So to mitigate this, uh, there are certain ways like we can have a different devices for WL and different device for the um, data, or maybe we can have a same segment size, because different segment size can cause the issues to like during the garbage collection. Then we have a llama and mindful stacking. In the last chapter, we have read about the BW trees. Um, so using this we can where it shows that stacking can helpful, because lot of this llama allows garbage collection and data management by itself. So this can help, this can benefit in lot of places. So this, yeah, hello.
Hi. Sorry, could you go back a bit? Like, there's a few questions. I guess me and someone else has about like file system logging.
Mm-hmm.
Well, maybe mine isn't a question. It's more of a clarification. But like, look, there's a question in the chat. Maybe if you could.
Okay, I will see chat.
Oh, no, all right. So so you said in the mitigation process, I don't know, like I said, it's just an idea. I don't know if it makes any sense. I'm like, if we have all these useless fragmented spaces, so what if we take all these fragmented spaces, kind of like make a table and like take the address of these fragmented spaces, log it in that table, and then we kind of like use that table. So I don't, like I said, I don't know if this makes sense, or maybe I'm technically describing a virtual page table or something. But yeah, when you keep track of that table and then you use that table to make it seem, you kind of join the spaces together to make a full space, and maybe you can use them that way. I don't know if that does make sense. Yeah.
Okay. Okay.
Say we,
Yeah.
sorry, say we have space 1 2 3 4 5 6 7 8 9, all right, and then
Mhm.
based on the file system login, we've taken space like 2 and 3, 5 and 6, and then 8 and 9, right? So we now have empty spaces like 1 4 and 7, and then we take those, because now they're fragmented, and let's say you need to make something. Now those 1 4 and 7 are kind of like fragmented, right? And then you keep track of these fragmented spaces 1 4 and 7 in a different table, like referencing this 1 4 and 7, and then you now try to use this 1 4 7 as a whole space on its own, so you can use
See,
1 1 and 4.
see,
Mhm.
the fragmentation, whatever I mentioned, right? It's not that much straightforward that you keep track of the um, places where this pages or whatever the
Mhm.
device we have, right, is empty, right, and we can put our data in there. It's not that much easy, because might be that much space we don't have. Let's say fragmentation space is available, let's say 3 KB, and our data is of about 4 KB. So how we are going to adjust that particular data, right? It will be still, we have to either partition the data and move up somewhere else.
Well, yeah, okay, well, that makes sense. Thank you.
Okay. uh, Anybody want to add in this one, llama and mindful stacking here? I think yes.
So I just hope like no one's confused, right? Like the core idea with like log stacking isn't really fragmentation is part of it, but the problem is that you have different applications. So you have your database on top, you have your file system down, then you have the like your hardware, like your SSD, which is and they're all using logs, right? And all their logs don't know about each other. So the problem is you have a buffer and then you have another buffer on different layers of the memory hierarchy, right? So that's where the problem is. You have like a lot of wastage because you're duplicating data, which could get like, as the CPU does what the CPU does, right? Like you end up with like a lot of wastage. So that's the core idea, and I hope
So,
that.
hey, I have one doubt here actually. So, as each layer is having their own buffer management, right? So, let's say database layer is collected like in a mem table. They have a accumulated data, and they are going to flush it, right? Once they flush it, it will go to the next layer, right? File system. Now, file system again, they will going to accumulate data and then flush it to the device, right?
Ah, so okay, so this is mostly with like the in-memory bit first, like, right? So like when you have like, let's say in the LSM, right, you have like the log that you're continually appending to like in memory, right? So that's space you've allocated. But depending on, so let's say you allocated that space, right? And you're maintaining it in memory. Your operating system might be doing something very different with that memory, right? Because you might have just gotten allocated virtual memory, right? So unless like you're doing like buffer management, right? And you're doing like uh, this is discussed in the, I don't know if it's in the slides, but there's like a direct hardware access you can do for SSDs, where you can just bypass like all these virtual memory segments and you can go straight to like operating on actual memory. So that's the,
Yeah, that they can bypass the whole this virtual memory thing.
yeah.
But
So
what my point is, yeah,
no, sorry, go ahead.
yeah. What my point is, let's say we have multiple layer, right? Then how it's going to manage the like, is it like one the flushes the data one from one layer to another layer, then another to layer to another
Yeah,
final to
exactly.
device.
That's kind of like the problem, right? That's the problem with
Hmm.
using like log structured, stuff, because you're layering logs on top of logs on top of logs, and that's bad. And those logs, each of those logs on each layer doesn't know about the other, so that's it's bad. It's a problem to be aware of, I guess.
Mm-hmm. Got it. Anybody want to add here in mindful stacking on Llama? Yeah?
I think it's an interesting idea. I didn't research too much about it, but I think the general gist is Llama allows for you to make consolidation changes based on like the methods that have been called on the tree or on the tree. So if I write to a node, like I write a key to a node and I delete a key from the node, like this thing allows me to know that writing and deleting means that this key should be absent. And so when I'm doing consolidation, like it is aware of that somehow. So I mean that's kind of the general idea I got, but I didn't research into how this actually works.
So, but basically, they took the example of the BW tree, right?
Yeah.
So, in last chapter, we have read the BW tree. Basically, it is like a LSM tree only, but each node will have the delta node appended to each every time, right?
Yeah.
So, at a certain point of time, we need to accumulate all the delta node and to merge it in the final node. So, this all the process, right, requires a garbage collection and accumulation. These all thing is this consolidation and garbage collection, everything is handled by this llama. So we don't have to worry about the whole thing. It's being handled by some different layer, like this layer. And that's why it's mentioned here that if we carefully consider, like we design our system, right? So stacking has many benefits. You don't have to worry about a lot of um, functionality you need to implement.
Yeah, cool. I think I need to do some more research in general, I think, on the idea. But yeah, this is enough for me to go by today. Thanks.
Thank you.
All right, thanks so much, Prakash, and thank you everyone for joining. See you. Oh, I guess small announcement I'm going to announce later, I guess, on the group. So Alex, the author of the book, is going to join us next week to review part 1. So with this, we finished part 1 of the book. So please prepare your questions. That should be fun. So I'll announce it on the channel so that people can prepare questions ahead from part 1. I think this is a good time to bring all of the questions we've not been able to answer in the review club. So yeah, just you get the information first since you attended today. So thank you. All right, have a good evening, good day, wherever you are. Bye.